Okay, let's dive right into this. Welcome to this explainer, where we are going to unbox the fuel cell revolution together. We hear a ton about fuel cells being this magical answer to clean energy, but today we're going to completely demystify them. We're going to start with the high-level concepts of how they actually work, and then we're going to get our hands dirty exploring the real-world math and physics. It's going to be a fascinating journey from chemistry all the way to practical engineering. So here's our roadmap for today. First up, the direct power revolution, then inside the fuel cell. After that, efficiency and real losses, and finally, scaling up to reality. All right, let's kick things off with Section 1, the direct power revolution. Think of conventional combustion as this incredibly clunky four-step process. You take chemical energy, you burn it to create heat, you use that heat to create mechanical motion, like spinning a massive turbine, and then finally, you generate electricity. Every single step in that chain is basically a middleman taking a cut of your energy. But with a fuel cell, it's just two steps. We go directly from chemical energy straight to electricity. No burning, no spinning, literally no moving parts. It's a direct, highly efficient line of power. Because of this super direct process, fuel cells bring some absolutely incredible perks to the table. We're talking secure, continuous output, zero emissions, and massive modularity. You can pretty much place them anywhere. But, well, here is the engineering reality check. The truth is, they do come with a pretty high cost, and crucially, they cannot respond quickly to electric load transients. Basically, if the grid demand spikes suddenly, a fuel cell just needs a minute to catch its breath and ramp up. Moving right along to Section 2, inside the fuel cell. Okay, let's get a play-by-play of the actual chemical action. At the anode, hydrogen gas flows in. Now, the fuel cell acts kind of like a microscopic bouncer, stripping the electrons right off those hydrogen atoms. And because those electrons are physically blocked from traveling through the electrolyte in the middle, they are forced to take a detour up and through the external wire. That flow of electrons right there, that is literally our electricity. It's just an incredibly elegant play. So, to break it down, this all happens in 4 beautifully structured stages. First, hydrogen flows over the anode. Second, electrons are stripped and pushed through that external circuit to give us our power. Meanwhile, stage 3, the remaining hydrogen ions move directly through the electrolyte while oxygen is introduced on the other side, at the cathode. And finally, stage 4, the ions, electrons, and oxygen all meet back up and combine. And the absolute best part, the grand finale, zero-emission byproduct of this entire chemical reaction, is literally just pure water. Let's shift gears a bit for Section 3, efficiency and real losses. Now, when we map cell voltage against current density, we hit our ultimate reality check. There are 3 distinct loss zones we have to deal with. First, that steep initial drop is the activation loss region. Think of it as an energy tax you pay just to get the chemical reaction started. Then, that long, steady middle slope is the ohmic loss region. That's just basic electrical resistance. And that steep cliff at the very end, that's the mass transport loss region, which is what happens when the system literally can't pump gas into the cell fast enough to keep up with the demand. But let's put this into perspective using a typical polymer electrolyte membrane or PEM fuel cell. How do all these losses actually impact the bottom line? Well, even with those pesky loss regions we just talked about, the fuel cell's thermal efficiency still absolutely crushes a traditional internal combustion engine across entirely different load levels. It's a massive upgrade. And if you're an electrical engineer, this next part is going to be your aha moment. All those complex chemical losses we literally just went over, we can actually map them out as a simple electrical equivalent circuit. The activation and concentration losses just act like resistors. But check out the capacitor right in the middle. That represents the double-layer charging effect happening inside the cell. It acts like a tiny little battery within the system, momentarily storing charge, and that perfectly explains why fuel cells can't just instantly react to sudden massive changes in power demand. Okay, let's look at some totally counterintuitive math straight from the source data. Let's say you're trying to optimize your fuel cell. You increase the cell's membrane area by 20 times, and thanks to some fancy new materials, you drop the resistance to just 1/10 of what it was. Sounds like a massive win, right? Well, scratch that. Let's run the math. Ohmic loss is calculated as current density times resistance times area. In our optimized scenario, you multiply 1/10 of the resistance by 20 times the area, and you actually end up doubling your total ohmic losses. It just goes to show that you absolutely can't just scale these things up blindly. which perfectly tees up Section 4, Scaling Up to Reality. I want to give you a really cool mental anchor right now, 80. If we assume each individual fuel cell operates at roughly 0.6 volts, it takes exactly 80 of these cells physically wired together in series to generate the 48 volts DC you'd need to continuously power a typical US home. One single cell is a fun science experiment, but 80? That's a legitimate power plant for your house. Let's actually run the numbers on that. To get 1,000 watts, or 1 kilowatt, to run that home, how big does this cell membrane actually need to be? Well, first we calculate the current. 1,000 watts divided by 80 cells divided by 0.6 volts tells us we need 20.83 amps flowing through each and every cell. Next, we apply the specific voltage formula, plugging in our 0.6 volts and 20.83 amps, and we find out the required membrane area is exactly 20.83 square centimeters. I love this because it completely grounds those abstract textbook equations right into physical reality. It tells an engineer exactly how much material to cut to turn your lights on. And this brilliantly illustrates a really hard truth. Fuel flow dictates your output, period. If you look at the relationship between power and the amount of fuel being fed, whether it's 25%, 50%, or 100% capacity, the maximum power point is completely constrained by your hydrogen supply. If you only provide 50% flow, the cell simply hits a brick wall at about 5 amps. You literally cannot draw more current than you have fuel for. Finally, let's zoom all the way out to the macro level. How do we take these 80 cell stacks and power a whole neighborhood or a whole city? Well, because fuel cells spit out direct current, or DC, we have to process it. Individual fuel cell units pass through independent boost converters to step up the voltage. Then, they are combined and run through a 3-phase inverter to convert that DC into alternating current, or AC, which is what the grid actually uses. This whole setup is what makes fuel cells a truly modular, flexible, grid-level power plant. We have covered a lot of ground today. We've gone from the microscopic swapping of electrons all the way up to massive grid-level inverters. We've seen the elegant two-step chemistry, but we've also faced the harsh engineering realities of ohmic losses and transient response times. So I want to leave you with this thought. With absolute zero emissions, highly efficient direct energy conversion, and pretty much endless modular scalability, are fuel cells the missing link in our clean energy future? Thank you so much for exploring the math and the magic behind this incredibly cool technology with me today. Keep wondering, keep calculating, and I'll catch you in the next explainer.